today we're going to start in on Chapter 7. Chapter 7 is about alcohols, phenols, and thiols. So this is pretty much pattern for the rest of the semester is going to be, here's a new functional group. We're going to learn how to name it, learn some reactions of those functional groups. So again, this chapter, we're going to be focusing mainly on alcohols. I'll also show you what phenols and thiols are as well. All right, but alcohols are going to be kind of the main focus here. All right, so what is an alcohol? An alcohol is anything that has the functional group OH. All right. We also call this oftentimes it's just referred to as an OH group. Formerly, it's called a hydroxyl group. All right, but an alcohol is any organic molecule that has that OH group in it. Okay, so an example, simple example here would be something like this, right? This would be our alcohol here, and you see that that OH group is always explicitly written. Okay. One thing I want to point out, because we've seen it before a little bit, is something like this, where you have that OH group bound to this carbonyl carbon here. This would not be considered to be an alcohol, even though it has that OH group. When that OH group is bound to a carbon that has that oxygen double bond on there, this thing gets its own name. This is what we call a carboxylic acid. Okay, and we'll learn about carboxylic acids at some point. That's another functional group that we'll introduce here. But again, just to point out, even though this does have an OH group in it, it's not considered to be an alcohol. It behaves very differently than alcohols do. Okay, so again, not this one here, but this over here would be considered an alcohol. A thiol, which we won't talk quite as much about. They're not quite as common, but nonetheless, we'll introduce this here as well, is something that has an SH functional group. Notice where sulfur and oxygen live on the periodic table. Oxygen lives right on top of sulfur, right? So they have very similar bonding patterns. They have the same number of valence electrons. We know that the periodic table is kind of arranged that elements that sit on top of one another that live within a column have the similar properties. So thiols behave very similar to alcohols, okay? But instead of an oxygen, it's a sulfur in there. So again, an example would be something like this, but now it's an SH group in there.
So thiols have that SH instead of OH.
Correct. Yep. And again, we're going to focus mainly on alcohols, but this is just to introduce these functional groups here. And then a phenol is actually a type of alcohol, but it's sort of very specific. A phenol is when you have an OH group bound to a benzene ring. All right, so like alcohols would be this broad class of molecules here. We see phenol as this specific example here, where you have an OH group that's bound to a benzene ring. Cool, so these are our three functional groups. Again, you're going to see we spend a majority of our time is going to be talking about alcohols, but these are our three new functional groups here: alcohols, thiols, and phenols. Okay, so the first thing that we're going to talk about is classification of alcohols, right? We've talked about how carbons, we can designate them as primary, secondary, tertiary carbons. Same thing with our alcohols. All right, so looking at alcohols, we want to be able to categorize them as primary, secondary, or tertiary alcohols. When you're characterizing an alcohol as primary, secondary, or tertiary, you're looking at the carbon that that OH group is bound to and counting how many carbon neighbors it has. Okay, so really a primary alcohol is when the OH group is on a primary carbon. A secondary alcohol is when the OH group is on a secondary carbon, et cetera, et cetera. Okay? So let's look at some examples here and see if we can't classify them. We'll do this first one that I did before. Oops. All right, so what do we think this first one is? Primary, secondary, or tertiary? Secondary, right? So if we're going to look at the carbon at the base of that OH group and just count how many carbon neighbors it has. So in this case, this one is a secondary alcohol. What about this next example? Yeah, so it doesn't really matter what's happening in the back half of the molecule, right? It's just, we're looking at just that carbon that has that OH group. That carbon only has one carbon neighbor. So this one is a primary alcohol, right? There's a bunch of branching going on happening away from that OH group, but that's not going to affect whether our alcohol is primary, secondary, or tertiary. And then this last example here, 1, 2, 3 carbon neighbors, so this would be a tertiary alcohol. Okay. The OH group, so if we sort of look at our OH group here, this is a very polar bond. Okay, so alcohols would be considered to be polar. Because of that, they can undergo what's called hydrogen bonding. That's what's being sort of illustrated here. This is interactions between neighboring molecules. So the word hydrogen bonding is a little bit of a misnomer. There's not any covalent bonding that I'm talking about here. I'm talking about interaction between neighboring alcohol molecules. Okay? It turns out that when you have a very polar bond with hydrogen, polar bonds do what polar bonds in general like to do, and that is that they line themselves up such that the positive end, the partial positive end on this hydrogen is going to be talking to the partially negative end of a neighboring oxygen molecule. Right? So in general, polar molecules will line themselves up right there. So first of all, I guess just take a step back. What the heck does it mean to be polar? Polar means that there's an unequal distribution of electrons going on. So when I say that this OH bond is polar, what I mean is that there's an unequal distribution of electrons. That oxygen atom is holding on to a lot of electron density and leaving that hydrogen with relatively few electrons. Right? So that's what all polar bonds mean, this unequal distribution to electrons. Somebody's holding a lot of the electrons, the other one isn't. Right? And so we say that gives this bond has this partial negative charge on this oxygen, leaving a partial positive charge on the hydrogen. Okay? And so what happens with polar molecules in solution is they all kind of line themselves up such that the partial positive end of one is talking to the partial negative end of a neighboring molecule. It turns out when that bond has hydrogen in it, it's even more special and gets this special name, hydrogen bonding. Turns out that these are strong, very strong compared to normal like dipole-dipole interactions. Okay, so if we had something like carbon and oxygen, this would also be a polar bond that has this partial negative charge and this partial positive charge. They will also sort of line themselves up in solution that way, but one of these isn't hydrogen, so it turns out that these hydrogen bonds are just this extra special form of these polar interactions. Again, you got hydrogen being involved, they just turn out to be a lot stronger, so they get their own name, hydrogen bonding. Okay? Bottom line is alcohols can undergo these hydrogen bonding because of the nature of that functional group, that OH group. So they form relatively strong interactions compared to other organic molecules that we've seen are alkanes or alkenes. Alcohols have a much higher boiling point because they have these strong hydrogen bonding interactions. Also in terms of, solubility, the solubility of these in water. We see that our smaller alcohols, so the difference between these is number of carbons. All right, so we'll get into naming here in a second. But methanol, how many carbons do we think are in methanol? One, right? So that prefix meth meant that in terms of number of carbons, there's one. What about ethanol? Propanol. 3. Butanol is 4, right? So those were our prefixes. We're going to go start talking about nomenclature again. So we want to remember what nomenclature we've learned from alkenes and alkanes and alkenes. Meth was 1 carbon. Eth, 2 carbons. Prop, 3 carbons. Bute, 4 carbons. And then it gets a little bit easier because it borrows from geometry, right? So pent is 5 and hex is 6. Hept would be 7. All right, so what this chart is showing here is that, let's focus on this column right here. Okay, it shows that our smaller alcohols are completely soluble in water. And then as that carbon chain grows and grows and grows, they become less soluble. Right, so propanol has 3 carbons, butanol has 4, pentanol has 5 carbons, etc. And so what's happening here is you have one half of the molecule, this OH bond, which is really polar. It can interact with water really well. But then you have the back half of this molecule, which is relatively nonpolar, right? We know our alkanes are nonpolar. And so as that back half, as that nonpolar end grows, the solubility in water decreases, right? Again, they all have that polar OH group, but there's like these dueling forces between the front half and the back half of the molecule. The OH group likes to interact with water. It's nice and polar. But as that carbon chain grows, as that back half grows, it'll be increasingly less soluble in water because this part's nonpolar. This back half here is nonpolar. Okay, so these hydrogen bonding are an important force in alcohols. Again, alcohols have a relatively high boiling point compared to all the other functional groups that we've studied thus far because they can form these hydrogen bonds. Okay, and actually, so on this hydrogen bonding topic, we got to know some terminology here. So again, by hydrogen bonding, these are interactions between neighboring molecules. Again, this is we have a oxygen that's partial negative, a hydrogen that's partial, that's not a negative. Hydrogen that's partial positive, and again, when we're talking about hydrogen bonding, we're talking about the interactions between neighbors. So this right here, the hydrogen of one molecule interacting with the oxygen of the other, that is our hydrogen bond. Okay? The hydrogen, so now more terminology here. The hydrogen in this hydrogen bond, we call the donor. And the oxygen, we call the hydrogen bond acceptor. Okay. And importantly, H bond acceptors can be any oxygen or nitrogen with lone pair electrons. right, so in our hydrogen bond, we call the hydrogen the donor, we call the oxygen the acceptor, and really any oxygen or nitrogen that has a lone pair can be considered a hydrogen bond acceptor. So certain functional groups will have hydrogen bond acceptors, but no donors. Okay, so anyways, we want to be able to, looking at a molecule, be able to identify whether it's going to engage in hydrogen bonding, whether it has a hydrogen bond donor, and whether it has a hydrogen bond acceptor. So I guess let's also just H bond donors.
What are they donating? Just the bond, or it's not an electron, it's positive, right?
No, it's not electrons. It's this interaction between neighboring molecules that we call hydrogen bonding, right? Polar hydrogen, the partial positive hydrogen interacting with the partial negative oxygen. And then we have names for who's doing what. The donor is the actual hydrogen, and the oxygen is the acceptor. So it's just kind of more terminology that's being thrown around these particular bonds. Turns out that hydrogen bonding is like one of the most dominant forces in biochemistry, right? So your two strands of DNA are being held together by hydrogen bonding. Proteins are held together by hydrogen bonding. So it turns out that when you go a little bit further into biochemistry, these hydrogen bonds play an absurdly important role, which is kind of why they have their own special name. All right, and so hydrogen bond donors, these are hydrogens in bonds with oxygen and nitrogen. All right, so we didn't talk about any hydrogen bonding with our alkanes because those are carbon hydrogen bonds. So the hydrogen has to be bound to either oxygen or nitrogen, a good electronegative element. All right, so now the fun part, nomenclature. So let's just review, because if we don't have this down, we're kind of screwed moving forward here. Again, those are our prefixes that indicate the correct number of carbons. Right, so 1 carbon was meth, 2 carbons was F, 3 carbons was prop, 4 is bute, 5 is pent, 6 is hect, 7 was hept. Does anybody remember what 8 is? Oct, yep, so again, kind of just borrows from, what's it called, geometry. 9 is non, and 10 is dec. Okay, so these, just like when we were naming alkanes, these prefixes are going to be really important. Now that we're talking about alcohols, what we're going to change is that suffix. Okay, so let's just remember here. We had 4 carbons, what did we call this? Without any other special functional group going on in there. So this would have been butane. All right, if we have 4 carbons, but now an OH group, this is butanol. Okay, so we give alcohols this suffix -ol. Not only that, but just like with our alkenes, we got to indicate the position of this functional group. So butanol isn't quite enough to uniquely name this molecule. I got to tell you which carbon it's on. And so I'm going to start counting. 1, 2, 3, 4. Remember, we're going to number our parent chain in such a way that gives our OH group the lowest possible number. So you can always number your parent chain both directions, right? And then the numbering scheme you're going to pick is the one that gives that OH group the lowest possible number, the functional group the lowest number. So in this case, this would be 1 butanol. Okay, everybody take a second and draw me 2 butanol. right? 2-butanol would have the OH group on that second carbon. I don't know why, but I have a bad habit of drawing my molecules right from left. It would 100% be equivalent like that as well, right? Those are the same molecule, just picked up and flipped upside down like a pancake. So remember, the orientation on the page is not what's important. All right, so let's do some practice. We'll kind of escalate in complexity here, introduce those alkyl groups as well, but let's just kind of make sure we got this down. So take a second and name the following molecules for me. All right, so let's go through these. So again, you got to find the parent chain. That's step one. So I guess if we want to review our nomenclature strategy here. Step one is find that parent chain, the longest continuous set of carbons. All right, so in this one, I have these 1, 2, 3, 4, 5. And you're going to name the substituents. In this case, I have this OH group, so that's going to get that all suffix at the end. Step 3 is to number that parent chain. 1, 2, 3, 4, 5. You can always do both directions and pick which one's correct. 3, 4, 5. Obviously, after a while, you get pretty good at seeing which one it should be based on, the position of the functional group. In this case, either one would be equivalent. They both put that OH group on carbon 3. So this would be 3-pentanol, right? Because there's 5 carbons in my parent chain, so it's pentanol. Okay. Likewise here, 1, 2, 3, 4, 5, 6 carbons in my parent chain. And where's that OH group?
1.
Carbon 1. So this would be 1-hexanol. Right? Important that you count the carbon at the base of that OH group, but there's not a carbon like over here, right? I think it's pretty easy to, once we start introducing functional groups, to accidentally miscount. So you want to convince yourself that there are indeed only 6 carbons in this molecule here. All right, so now on this next one, now we're starting to introduce some branch points here. So this starts to get a little bit tricky. Again, the strategy is the same thing. We're going to find our parent chain, the longest continuous set of carbons. So 1, 2, 3, 4, 5. So in terms of my substituents that I'm going to name, this one is my alcohol group, going to get that all suffix. But I have to make sure to include this carbon here in the name too. So how am I going to do that? Do we remember how to do alkyl groups? Right? So methyl, right? So if we're just going to name this one right here, there's 1 carbon, meaning that this substituent is a methyl group, right? It's outside that parent chain. I still got to make sure to include it in the name. The entire logic of all this organic nomenclature is that it uniquely points to one molecule. So all the carbons, all the functional groups are accounted for in the name. So my name, my parent chain is the pent, but I still got to make sure to include this in there as well. So this would be, now we're in a number. Okay, and importantly, so we're going to sort of update this name number parent chain rule to make sure we prioritize the OH group. Meaning you're going to pick the numbering scheme that gives that OH group the lowest number. So I'm not looking at the methyl group at all when I'm numbering. I'm only making sure to pick the numbering scheme that gives my OH group the lowest number. So I'm still going to include it in the name. So this would be 4-methyl 2-pentanol. I got all those carbons accounted for. All right, so given what we just discussed, take a second and try to name this one for me. All right, so how many carbons are in my parent chain? 7, right? So it's going to be a heptanol. 1, 2, 3, 4, 5, 6, 7. I got to name my 2 substituents. Again, this is that alcohol group, so it's going to get that all suffix. And I still got to make sure to account for this carbon over here, which will be a methyl group. All right, and then I'm going to number in such a way that prioritizes that OH group. So let's put them both down. So which one am I going to do, my red or my blue? Red, right? I'm going to do the one that gives the OH group the lowest possible number. So this is 6-methyl 3-heptanol. All right. All right, so these ones are a little tricky because that first step, that find parent chain step, I made it a little bit more difficult here. Remember, it's the longest continuous set of carbons, all right? So my parent chain in this first example, actually I'll use colors, right? Everything's going along great, but those are my parent chain. That's the longest continuous set of carbons, right? So it's very tempting to just always do the ones that are sitting in a row. But this would mean my parent chain has 1, 2, 3, 4, 5, 6, 7 carbons. And if I went the other way, I would have 1, 2, 3, 4, 5, 6, 7, 8. So I have to choose that longest continuous set of carbons. All right, I'm going to name my functional groups. Again, my OH group is going to get that all suffix. But I have to account for these 1, 2 carbons right here. So what would I call this substituent? An ethyl group. All right, and then I'm going to number my parent chain. So that ethyl group is on carbon 5. 5 ethyl, 3 octanol. All right, so remember to find that longest continuous set of carbons. You can't just default to thinking it's always going to be, the squiggly line. All right, so same with this one here. I don't know what happened to my bar. But I'm going to find my longest continuous set of carbons. 1, 2, 3, 4, 5. Okay, it would have been equivalent if you counted in this direction as well. You get the same answer. Okay, so then I'm going to number my parent chain. Well, I guess to name my substituents, again, this is an all group, and this is, again, I'm not very creative, an ethyl group, right? 2 carbons. So numbering my parent chain, I'm going to start out with that OH group to give it the lowest possible number. So this is 3 ethyl, 1 pentanol. Cool? Right, so again, we're sort of just piggybacking off of our rules for nomenclature of alkanes and alkenes. Now we've just introduced a new functional group, the alcohol group, and that gets that all suffix. All right, let's just do a little bit more practice here so we can remember some of the other rules about our nomenclature. All right, so what's my parent chain in my first example? How many carbons? 5. So 1, let's use color. 1, 2, 3, 4, 5. So now I'm gonna have like an interesting problem when I go in and number. Right, 1, 2, 3, 4, 5. If I go the other way, 1, 2, 3, 4, 5. Remember, the whole logic is I'm going to prioritize that OH group, right? But in this case, both of those numbering schemes puts that OH group on carbon 3, right? So in order to break this tie, I'm going to look at my other functional groups, my methyl groups. So actually, the blue numbering scheme is what I'm going to go with here, right? Since both of them put that OH group at the same one, I'm going to pick the one that has the other group at the lowest number. So again, my blue numbering scheme is the one that's correct here. It is tricky. Okay. And now I have 2 of these methyl groups right here. So when I name this, this is going to be 2,2-dimethyl. You have to put the location of both of those methyl groups, even if they're on the same carbon. Right? So I have to have 2,2-dimethyl in my name, indicating the position of both of those methyl groups. All right, so it's not just 2-dimethyl, it's 2,2-dimethyl. Dimethyl 3-pentanol. Okay, so why do we have to include both of those in there? Because take a second and draw me 2,3-dimethyl 3-pentanol. All right, so I've got my 5 carbons in my parent chain. I have one methyl group on carbon 2, another methyl group on carbon 3, and my OH group is also on carbon 3. All right, so so we can see 2,2-dimethyl 3-pentanol and 2,3-dimethyl 3-pentanol. Right, point being is we got to indicate the position of both of those methyl groups when we say dimethyl. Super common mistake is to just say 2-dimethyl 3-pentanol or something like that. All right, so make sure to include them both. This next example also has one of the easier rules to forget about when it comes to nomenclature here. All of this we've done before, but it's been a hot minute since we've done nomenclature, so let's just make sure to review all the little intricacies here. First of all, how many carbons are in my parent chain? Yeah, so I have 1, use green, be consistent, 4, 5, 6, 7, 8. I'm going to name my substituents. Again, my alcohol group gets the all suffix. A 1-carbon group is again a methyl group. And then what would I call this 3-carbon branch right here? Propyl. Right, so it's that same prefix, but when it's not on the parent chain, you put that YL ending to it. Right, so methyl, ethyl, propyl, butyl, etc. I'm going to number my parent chain. Okay. So it's, right off the bat, we can see that this is going to be a 3-octanol, right? Importantly, again, this example specifically wanted to do it because now that we have 2 substituents, when we put them in our name, we're going to make sure to put them in alphabetical order. So I have a methyl group and a propyl group. When I assemble my name, I'm going to put them in alphabetical order, which means LMNOP. The M comes first, right? So this would be 7-methyl 4-propyl 3-octanol. Okay. The last thing we want to be able to do, again, kind of just review from previous, is what happens if we have a halogen in there. All right, so we find that longest continuous set of carbons. 1, 2, 3, 4, 5, 6. We're going to name our functional group. So again, that OH group gets that ol suffix. What do we call the fluorine? Fluoro. And what about the Br? Bromo. I'm going to number 1, 2, 3, 4, 5, 6. And again, when I assemble my name, I'm going to make sure to put these substituents in alphabetical order. So the bromo gets listed first. 3-fluoro, 2-hexanol. Cool? All right, so next time we'll pick up with reactions of alcohols. This gives us up to our nomenclature here.